Go ahead,
Uh,
Aamir.
Hi everyone. Today we will be discussing the paper titled Bayesian Learning of Occupancy Grid. This was published in 2020, and oops. Okay, so the paper essentially tries to predict or generate the map of the environment given a series of measurement. The paper is divided into sections, and the first section like derive this general formulation that is essentially a updation rule, a Bayesian updation rule used to generate the map. The second section talks about a couple of approximation to the general formulation to make the simulation or the finding the result much more computationally less complex. And lastly, they put forward two toy problems and a simulation where they showcase the equation working. So so this is mainly a theory paper. So before going to the theory proper, uh, like, okay, so there are a couple of uh, terminologies that's used in the paper. So first one is that the environment is considered as a grid of cells, and it is indexed by the letter I, and the CI stands, the I here stands for a particular coordinate xi, y, and zi, and the map is defined as a vector of length b, and each element of that vector can be either 0 or 1. When b equal to 1, it means that that particular grid or particular cell is occupied, and when it is 0, it means it is empty. Uh, and the other definition is that of measurement. So the entire measurement is considered as a matrix where each row of that matrix uh, is the uh, okay, is the measurement taken at a particular time s, and each single measurement is a vector again, is a vector of length k, and it can be either 0 or 1. K here also encodes the some position where that sensor is directing and picking the data from. And the measurement can again be only 0. It is binary. Essentially, it means that the sensor detects something over there or it didn't. So the problem statement essentially boils down to finding the probability of a particular map given a series of measurement. And one like argument that they had talked about in the paper is that the previous work had all assumed the uh, map to be like independent. So the probability of B would be the like product over BIs. And they also mentioned that there is one another work that had considered this independence, but that particular one didn't consider measurement to be vectors. So that one had measurement to be scalars. And the output of this algorithm would be the marginal posterior, where they, okay, so for a particular cell, what is the probability that that cell is occupied given the previous measurement? So that's what the equation is basically trying to find out. Before going to that derivation, there is one more one more thing that they had used, and that is the binary asymmetric scanner. So essentially, it captures how uh, each grid BI influences the measurement at a particular location. So how they model that is that okay. So for each grid, there is a chance that it can be viewed as a it can be viewed as it is, or it can be flipped. So they introduce this B tilde over here, and then essentially what they are arguing is that the sensor sees the map B tilde instead of the B, and okay, so if there is any B tilde where B tilde is 0, then sorry, B tilde where B tilde is 1, then that JSK would be 1 as well. So it's basically a Boolean summation over B tilde. And okay, so see, so far, like I haven't talked about any like physical nature of the sensor measurement or the environment or thing, because mostly that physics is encoded in the transition probabilities over here. So it will mostly depend upon the problems at hand, and that's how they model the interaction between grid cells and the measurement.
So, are you talking about the error introduced by this? I'm trying to understand what this PFA.
Yeah,
it's like kind of there is a real distribution, and then there's some error generated by some process.
Okay, so from what I understood, it is okay. So so suppose a sensor is measuring the like occupancy of a particular grid, and that occupancy would be influenced by the entire grid, and that is what they are doing here.
I mean, my question is like, is this a model of a noise, or there is
the
basically a model of a noise? Okay. And what does BAC stands for?
The BAC is the binary asymmetric channel.
Okay.
Okay, so to the derivation, okay, so the first, the equation number 1 is the definition, standard definition for conditional probability, and then expanding JS to be current measurement plus previous measurement. It can be written as equation number 2. Okay, so here BR equal to 1 is replaced by the summation, where B is taken, B belongs to the entire set of map where rth element is 1. And then using same rule and reducing the equation, okay, so it can be written as this. And here they again make one more assumption, and that is to say that the probability of JS given B intersection JS minus 1 equal to P of JS given B. And from like, I'm not sure about this, like what this assumption is, but what I think is that they are basically assuming that the environment is static. Like if that is
hold
not.
On. First of all, I don't understand what's the difference between capital J and lowercase j.
Okay, so capital J over S is what we initially had. Lower JS is the current measurement. So
capital J is all of the previous measurement of the signal. Okay, and JS is the current measurement of the signal. Okay, and signal, and B is the measurement, right? So J is the signal, or
B is the map.
The actual location of okay.
So the
and then this one means that this conditional probability is independent on all of the previous measurements. Well, that makes sense, right?
But does that mean that the environment is static, or like
no, it just doesn't mean, it means that it's only the location of the object that determines the signal. There's no memory.
Okay. So then like they substitute this to the previous equation, and then like identify this first term as a normalized constant. Okay, so then okay, so this is the marginal posterior, and the full joint posterior is given by this particular expression. Okay, then I believe this equation also comes from their previous assumption, right? That Pjs given B equal to a product over Jsk given B.
What is the second? Okay, probably the
S is the time. Like,
S time and K is the location. Yeah. So no, here the factorization property of the conditional probability. So it's similar to what they had above. I don't know what.
okay.
Yeah.
So then they are essentially then trying to find this particular term, and for that.
Yeah, it makes sense. Hold on. So if you go back, so basically, you have some B is your actual location of whatever you're trying to, and J is the signal, and so that's saying that whether the signal is 0 or 1 really only depends on B. And there is, signal of the nearby pixel doesn't affect on the grid, doesn't affect your signal. It's really B that determines it all. That makes sense too.
Okay, so then they are like trying to find this particular term. For that, they find the probability for JSK to be 0. But before, JSK is defined as the Boolean sum of B tilde. Like if any of the B tilde is 1, then JSK will be 1. So for JSK to be 0, the entire BA tilde has to be 0. And BA tilde is again defined by BI, right? So BI into some probability equal to BA tilde. So but with that, they are able to write this particular product as a probability as this product. And here, okay, so there are two probabilities here. The first one is when BI equal to 1, and the second one is when BI equal. Sorry, the first one is when BI equals 0, and the second one is when BI equal to 1. And then putting these into the equation number 5 and 6 for the marginal and the conditional, the full probabilities, they expand the terms into these two. So the first term, inside the product, the first term over here is when JSK is equal to 0, and that is the same thing as the one over here. And the second one is when JSK is equal to 0, sorry, 1. And essentially, once you have an initial P given JS minus 1, the previous one, then we can update the next one with this equation. So then they are basically using this equation to two problems. And before going there, they also introduce two approximations. One is to consider only a set of a subset of the actual grid while doing this summation. And the other one, in the paper, they mentioned that the range, the first one is called cone only. The second is called the range gate only. And they mentioned that the range gate only essentially limits the it is only looking at a particular range of the measurement, like in the J1 to K, only a subset of that is considered. I'm a bit confused about how these
Hold
two
on.
are.
So this is how they model the environment, right? As a grid, yes? And
Yes.
the point is that some cells will be occupied, some cells will not. But then you can do it two ways. You basically say everything in the cone is occupied, or only some.
No,
No.
no, like this is an approximation to finding this particular, like that is coming up next, like what how they are utilizing it, the equations. But this
Where
particular
is B? Where is B located? This is a space for B's, and then there is some signal comes. As far as I understood, maybe I'm wrong, that your detector detects J's, and from
yes,
J's you have to reconstruct where B's are occupied, right?
yeah, yeah,
And so and then you can have different models of what B's are given J's. Yes.
yeah.
Okay.
Okay, so like these two figures is an approximation of this equation basically. But
Okay.
like I'm not completely sure like how that happens. Okay, so for like there are two experiments that they had done, and for those two experiments, this is the probability that they used to find the B tilde. And
What are the four subscripts, two superscripts, and two subscripts mean? So P00 is like changing
like,
from 0 to 0.
yeah, if B is zero, then like the measured one is zero, and the other one is if B is one, then measured one is zero.
And K, I are the two indices of the grid.
Yeah, K is the indices representing where the where measurement location is like where the measurement is taken, and I the indices representing a particular uh, grid. Like
Okay.
yeah. And the distance is the function which like the distance between BI and where the measurement is taken.
Mm-hmm.
Okay, so with this two modeling, okay, so this is one of the toy example there. So the first one is the actual map of the environment, and this is like sampled into these JS. So each point can either flip or stay the same.
Mm-hmm. Mm-hmm. Okay.
So this is this is one JS, and a series of that is put into the
This is the detector, what's detected with some noise, right? So B is what. Okay.
and the GF is the full general formulation, and this is the occupancy curve that it predicted.
Mm-hmm.
And the CO is that one approximation that I previously mentioned, and it also predict this one. And the RGO is the other one. And the IM over here is basically when CO and RGO compresses down to a single grid. So essentially to say that each grid measurement is independent of the other one.
Mm-hmm.
And they are the claim is mostly that the population uh, uh, has better accuracy than the one like the one with the independence method.
Mm-hmm.
And there is a CM like conventional method that they use in the next experiment. But like for that they use a particular equation from another paper. And accuracy, the performance is measured using rho, which is essentially the cosine error. Like these are two vectors, like the predictor and the actual map, and the outer product over its norm. And then they also use a uh, uh, okay performance metric called the sum of the Jensen-Shannon distance. Like they like so yeah. So this is for the toy example, and then they also have a example consisting of a simulation of sonar like signals. Okay, for this they use use the simulation tool, And like this is the figure number A is the measurements, and figure B is the actual like the true occupancy rate of the environment. From here, they applied their algorithm to recreate using CO and RGO, and the other one, the one that they recreated using the equation, perform much better than the one where the good independence good dependence wasn't considered, and these are the performance metrics for that one. Thanks. If there are any questions or discussion that can be made, had with this paper, then you have.
So I have a question about this models of probability distribution, because it's a Bayesian approach, and you had models for P's for the noise. If you go back. No, the actual models. No. This I understand that there has to be some noise. Now, if you go further, maybe.
Sorry.
Yeah, this one. So where does that come from? Why is this a good model?
Okay, so they didn't specify the motivation or the how they derive this, even for this. Okay, so for this particular, no, sorry. Okay, so for this particular equation, the RGO one didn't use this equation, like that. They mentioned that for that they used another equation which was performing but much better than this one. The paper.
I understand, because this is a model of noise, right? This is what's most important thing here, right? This is the noise, kind of. Yes.
Yeah, essentially, every a particular system's dependence basically comes from this.
Well, anyways, if it's a model of noise, it would be nice to see how is it, for example, connected to the maximum entropy principle. Like, what would be the constraints that need to be imposed in order for noise to be like that? What is alpha, or is it just some kind of phenomenological model that has no theory behind it?
Okay, so the alpha they chose was number 2, the value 2. Again, they mentioned that it was mainly done through experiments, but again, I have to go through if there are any supplementary materials there they might have expanded on that, but in the paper itself, there was no mention of that.
And the other thing, that this loss looks like completely local, right? So you locally flip a given pixel, whatever.
No, BI renders the environment, right?
Right. But usually noise is non-local. Well, it is local, but it's not completely localized, and it doesn't completely factor into the product of probability distributions for flips. And so, if there's one part of your grid which noisy, then it's likely that the nearby places are also noisy, and so there has to be some kind of locality preserved. So but I don't understand. I don't think this would capture that because that's completely, well, unless I and K, or maybe so maybe they're not.
No, okay, so
They may be non-local. Okay, so no, I take it back. Here it's not clear how those P's are defined. For example, can be at one side be simultaneously flipped, and the other side, can there's one noise random variable affects the flips of two bins, two cells. I don't know. Okay, let's see. So what's the main conclusion is that the
main conclusion is basically that, okay, so the previous work had assumed that, okay, the probability of each grid is independent, and there in this particular derivation.
Oh, I see. And now they have dependence. I got it.
Yeah.
Okay, perfect. Yeah, that makes sense. And that helps, right, in reconstructing. Okay, perfect. Okay. Other questions? All right.
Okay, thanks.
Thank you. Thanks, Aamir.